Earth, a unique planet, restless and dynamic. Continents shift and clash. Volcanoes erupt. Glaciers grow and recede. Titanic forces that are constantly at work, leaving a trail of geological mysteries behind. This episode investigates the deadliest and most destructive volcanic event in U.S. history. Mount St. Helens, a pristine snow-capped mountain, suddenly blew 600 feet off her summit in a type of eruption no one had ever witnessed before. Scientists trying to understand what made this event so lethal uncover evidence for one of the biggest landslides in history, a sideways directed blast that knocked over 230 square miles of forest, and mega mud flows that thundered down the valleys and destroyed everything in their path. What scientists have discovered from this unique event brings geologists one step closer to understanding how the Earth was made. In Washington State, 100 miles south of Seattle, stands Mount St. Helens, one of 20 major volcanoes that form part of the Cascade Mountain Range at the North American West Coast. Before May 18, 1980, she was at the center of a thriving recreational paradise and prosperous timber industry.
The volcano had a beautiful conical form. It was called the Mount Fuji of North America, and the form was a bit concave.
But beneath her beauty lay an ominous secret. The mountain was brewing something that had a deadly potential. The story began on March 20th, 1980, when a 4.2 magnitude earthquake woke Mount St. Helens from a slumber that had lasted 123 years. The last known eruption was witnessed in 1857 by local tribes. In 1980, the earthquake was an alarming sign, because earthquakes may be an indication that an eruption is building up. Earthquakes can happen when magma rises from deep inside the Earth, shifting and breaking the rock on its journey up.
The very first signals we had were earthquakes at shallow depth beneath the volcano, and within a matter of just a few days it was clear this was something unusual. So the word went out to scientists around the country, and very quickly we started to converge at St. Helens and started trying to understand what was going on, and what we saw was the volcano was becoming more and more and more restless.
Volcanoes are dangerous because they are hard to predict. And in 1980, the science of predicting volcanic eruptions was still in its infancy. The most recent explosive eruption that occurred on the continental USA was Lassen Peak in California in 1915. Since then, most of the experience volcanologists had gained came from studying quiet lava flows on Hawaii.
Volcanoes are incredibly complicated natural systems, and they're always full of surprises. St. Helens surprises us all the time, other volcanoes surprise us, but we're learning.
Armed with the latest scientific equipment, volcanologists were anxious to study a possible eruption. Little did they know that they were about to witness the most deadly volcanic blast in the U.S. in living memory. On Coldwater Ridge, 6 miles northeast of the volcano, they installed a trailer with highly sophisticated equipment and began to closely monitor the mountain. From there, they had a perfect view over the volcano.
We had a front row seat to seeing the evolution and reawakening of a major Cascade volcano. And we were fortunate in that we had people here with a lot of energy. People were working 15 to 20 hours a day.
In addition to earthquakes, another key indicator for volcanic activity is gas emissions. Magma made out of hot molten rock contains gases that come from deep inside the Earth, 30 miles down. As magma moves up from these depths, there is less rock weighing down on it from above, so the pressure on the magma decreases. Gases dissolved in the magma escape and rise to the surface. But gases are not just a telltale sign of rising magma. They are also responsible for the explosiveness of the eruption. The greater the buildup of gas pressure within the volcano, the more explosive the eruption will be.
Well, this is a simple experiment to demonstrate the importance of gas pressure in a magma. The bottle is partially filled. This is filled about 80% with water. This will be simulating a volcanic eruption. So I'm going to carefully place the bottle here. We'll tilt it a little bit away from me. I'm going to put on my safety goggles. And now I'm about ready to start pumping. Here we go. Oops, there's a little bit of gas coming at the bottom. A little bit more. And the pressures are up to about 60 pounds per square inch. Whoa! Did we get it? We got it! Yeah!
Like in the bottle, the presence of gas at the surface of a volcano is a sure sign that an explosive eruption is building. In spring 1980, Casadaval's job was to detect these gas emissions. The gas he was looking for was sulfur dioxide. It's a gas that smells like rotten eggs and is associated with volcanic activity. But the key to the measurements wasn't the smell. The secret was subtle differences in the color of the light.
This instrument looks at the light in the sky, and it looks for the presence of certain molecules like sulfur dioxide, which also absorb light from the sky. And it measures the difference between the light absorbed by sulfur dioxide and the light available in the rest of the sky.
In March and April 1980, Casadaval and his team were using this instrument to detect the amount of escaping gases. They assumed that the gas levels would increase prior to the eruption as more and more magma would rise inside the volcano. But in 1980, the assumption proved wrong. Gas emissions didn't change even though earthquakes were getting stronger and hundreds of small tremors were recorded.
There was really no significant variation. It was a very low level of sulfur dioxide emissions, and there was nothing in those emission rates that really indicated that an eruption was just around the corner.
But by late April, after 5 weeks of tremors, the mountain gave them another clue to what was brewing inside. On the north face, a huge bulge was growing outwards.
A casual observer would look at the volcano and say, well, it's no longer a nice Fuji-type shape, but in fact the north side now is bulged out, and it was obviously deformed in some way. And we were trying to understand what could have been causing that deformation.
It was the first time scientists were able to monitor the deformation of a mountain. On Coldwater Ridge, they installed an instrument that uses laser technology to get precise measurements as to how fast the bulge was growing.
What we were trying to do was to focus a laser beam from this instrument on a reflector in the volcano, receive the return reflected signal, and then measure that distance.
The reflectors they used were small mirrors, about 3 inches across, they had fixed on the bulge.
As was the case in 1980, before May 18th, the north flank of the volcano was moving outward. It was bulging outward, and so the distance was getting shorter. And what we learned is that from Coldwater 2, that distance was getting shorter about 5 feet a day.
By May 11th, the bulge had expanded outward a staggering 450 feet. Jurishin had a hunch that it was caused by rising magma.
We knew that the north flank was deforming. We knew that something had to be causing it to deform. What could that be? Well, it could be magma forcing its way up into the volcano, shoving the north flank aside. That was a possibility. Well, what else could be causing it? Well, maybe the earthquakes were simply causing the volcano to become unstable as a result of gravity. Maybe there was just a slow landslide going on. It's very difficult to understand or to make a measurement that would tell you the difference. The plausible story was that magma was forcing its way up under the volcano.
As the bulge grew, the flank of the mountain became increasingly unstable. Still, scientists had no idea how deadly the eruption would turn out to be.
So we didn't know for sure until it happened. But as the bulge continued to grow, we knew we were getting closer to the final outcome. We just didn't know what that would be.
There were other signs that an eruption was imminent. Earthquakes became more frequent and stronger as time went on. Authorities feared the worst and zoned off the area around the volcano with limited access for the public. In spring 1980, geologists were dealing with a number of clues that Mount St. Helens was building to an eruption. Earthquakes were an indication that the volcano was waking up. Despite low and unchanging gas emissions, a growing bulge on the north face suggested that the magma was indeed on the rise. Mysteriously, after May 14th, the volcano quieted down. There was hardly any seismic activity, and the bulge grew at a slower rate. On May 17th, officials gave in to pressure and allowed some people with property inside the restricted area to gather up whatever they could. Another group was scheduled to enter for 10 a.m. the next morning. But on that day, disaster struck. On the morning of May 18th, scientists were about to witness one of the worst volcanic disasters in modern history. For more than 2 months, a team of volcanologists had been monitoring Mount St. Helens.
It's another reason why May 18 was a surprise, because basically all of this data we collected before, there wasn't anything that told that, May 18th was going to be the day.
David Johnston, a young volcanologist with the U.S. Geological Survey, was on duty that day. He had spent the night on Coldwater Ridge to carry out measurements of the growing bulge.
It's interesting that even on the morning of May 18th, the measurements that Dave made indicated that that bulge was still growing at about the same rate.
The same morning, Dan Miller was on his way to Coldwater Ridge to check on the time-lapse camera they used for filming the north face.
I was headed to the north on Interstate 5 out of Vancouver, Washington. And as I got a few miles north of town, there's a overlook point as you go down the highway where you can look off to the east and see Mount St. Helens. And I looked over there and it was a beautiful clear day, and there was Mount St. Helens with this giant mushroom cloud going up above it. At that point I knew something very serious was underway.
From a safe distance, 35 miles away, Miller witnessed how the eruption unfolded.
The first thing I did was went to our radio, our communications radio, and I made some calls up to Dave to try to raise him and find out what was happening. And not only did I not reach Dave, but even our repeater, which was on a mountain peak that was another few miles to the north of Coldwater 2, did not answer, indicating that it had been destroyed. And that was very scary. At that point I realized that something bad had probably happened to Dave.
Thick, dark smoke was billowing out of the crater, obscuring the view. Within hours, daylight turned murky gray and reduced visibility up to 300 miles northeast. It wasn't until 24 hours later that the air was clear enough for scientists to inspect the devastation.
The entire landscape was almost unrecognizable to those of us who had spent almost 2 months before the big explosion on May 18 working up there every day.
Suddenly I realized that there was complete and utter silence. There were no insects, there were no small animals, and there were no colors. The only color was ash gray, for as far as I could see.
We made our way up along the edge of the ridge and we found the small quarry where Dave's trailer and our vehicle had been parked on the morning of May 18th, and we could see that it was gone.
Neither Johnston nor the trailer were ever found. A total of 57 people were killed, along with thousands of deer, elk, bears, and other wildlife. 230 square miles of forests were destroyed, and the eruption had torn a 2,000-foot wide crater in the summit.
It was no longer a beautiful Fuji-type volcano. And in fact, we could see that the top of the volcano appeared to be missing or was obscured.
In the months to come, scientists faced the difficult task of finding out what exactly happened on that fateful day. They searched the ground for clues and methodically pieced together the chain of events that had led to the devastation. The first important clue was an earthquake measuring 5.2 that shook Mount St. Helens at 8:32 that morning. The second piece of evidence came from photographs taken by tourists who flew over the mountain around the same time.
They looked down and they were able to document by a series of photographs some shaking on the top of the mountain, and then right afterwards the whole front of that mountain started to move sideways.
In a series of still photographs, they documented how the bulge collapsed.
A magnitude 5.1 earthquake caused the north flank, which was greatly weakened by the deformation, to break loose in the form of a giant landslide.
The volcano just couldn't take it anymore, and the north flank became unstable and slid away.
Within seconds, 1,300 feet of the mountain slid down and destroyed everything in its path. What used to be a quiet mountain valley, with the Toutle River running through it, was now filled with debris up to 600 feet high, forming a hilly terrain known as the hummocks. From the amount of debris from the landslide, scientists calculated that 2/3 of a cubic mile of rock slid down the mountain, enough to bury Washington, D.C. under 50 feet of rubble. It was one of the biggest landslides ever recorded in history. It tore a gaping hole in the side of the mountain, almost 2 miles wide and over 2,000 feet deep. To scientists, it was a mystery why suddenly the entire northern flank of the volcano collapsed. Geologists today can still follow the trail of destruction.
What we're looking at here is part of a large debris avalanche. We're looking at one of the hummocks. And this is a rock outcrop that's actually outcropping in the hummocks. And the coloration that you see, first of all, is telling you that this has been altered.
This color provides an important clue to why the landslide became so big. Instead of the usual black of volcanic lava rock, it is yellow. This is a sign that the rock came in touch with hot water, turning some of the minerals in the rock yellow. Geologists found the same yellow rock in the crater wall, suggesting the discoloration must have happened on the mountain before the eruption.
So you have rainwater or glacial water that seeps down into the mountain, gets close to the magma, heats back up, and as it comes out of the mountain then it starts to change and chemically alter these rocks and turning them, into these different colors.
But the hot water didn't just change the color. More importantly, it also weakened the rock.
So you can see how crumbly these rocks are just by kind of digging your hammer through here. And the reason they're so crumbly is because when the hot water moves through and alters them, they sometimes alter to clay and some really soft materials. So if you took any other rock, it would be much stronger.
This yellow, crumbly rock isn't just found here, but stretches over 17 miles throughout the valley, suggesting that large parts of the mountain were rotten, weakened before the eruption.
So probably what had been happening over thousands of years is magma down on the volcano heating up water, and this acidic water was gradually rotting out the center of the volcano. It couldn't be seen anywhere at the surface.
When the bulge on the north side finally collapsed, it pulled along big parts of the rotten volcano and left behind the horseshoe-shaped crater St. Helens is famous for today.
This volcano is just a sand pile, if you will. It had very little internal integrity or strength, so that when failure did occur, literally part of the mountain slid away.
But more destruction was to come. Within minutes of the landslide, Mount St. Helens channeled her fury into another deadly force.
The air turned absolutely black, so nobody could see anything, but a few of these witnesses that managed to survive out on the very edge, the ground shook intensely, and they sensed that all the trees were coming down at once, even though they couldn't see it.
The landslide had spread east and west, but this force surged in a northerly direction. Within 3 or 4 minutes, it destroyed everything on Coldwater Ridge and ripped out trees in a 230 square mile fan-shaped area.
So even where we're sitting here, 8 miles from the volcano, You can see this ridge behind me. This ridge is 3,000 feet tall, and all the texture that you see on this ridge are the trees, the old-growth forest trees that were blown down by the surge that went up and over this thing like it wasn't even there. And so for the surge to have gone up and over this, it had to have still been going at roughly 300 miles per hour, and then it continued 9 miles further than that before it finally stopped.
To geologists, this was a surprise. They had never witnessed a sideways eruption before. Scientists were intrigued as to what had caused this devastating surge, so they began searching the ground for evidence. 5 miles northeast of the crater, Waite is revisiting the old deposits. Mixed with burned wood from the shredded trees, he also finds rock. To the untrained eye, there is nothing unusual about it, but not so for the experts.
It's clearly young rock. It's relatively light, and there's lots of little voids in here. In other words, little bubbles that are frozen in the rocks. So this was the rock that was growing. There's a hot liquid, almost solid liquid, that was growing inside Mount St Helens and causing the bulge before May 18th.
This small rock was a crucial piece of evidence for scientists trying to figure out the chain of events. After the landslide tore a gaping hole into the north flank of the mountain, it exposed the magma underneath. Without a cap of earth to keep it sealed, the magma suddenly expanded and surged outwards, pulling along rock from inside the mountain.
You can envision it as sort of a colossal-sized ash hurricane. It was a cloud of rocks and ash and hot gases that was maybe several thousand feet thick, that was moving across the countryside at speeds of several hundred miles an hour. A very turbulent mixture with blocks as large as 3 or 4 feet in diameter flying through the air. It was incredibly destructive.
After the initial surge, Mount St. Helens turned quiet. For half an hour, there was calm and tranquility. Then, the volcano began hurling its fury skywards. An enormous mushroom cloud formed high above the volcano, 3 times as tall as Mount Everest. Ferocious explosions went on for hours, releasing huge amounts of energy equal to 27,000 Hiroshima-sized atomic bombs. What happened on May 18, 1980 became a landmark event for scientists. It provided them with an unprecedented chance to study a lateral eruption. Discolored rock in the valley and in the crater wall were evidence that the mountain was rotten before the eruption. Gray volcanic rock 9 miles north of the volcano was evidence that the landslide uncorked a massive lateral blast. At 5:30 in the evening, the volcano began to slow down until it finally quit. But there was more impending danger, as the eruption had caused another cataclysmic effect. On May 18, 1980, Mount St. Helens exploded in a type of eruption never witnessed before. One of the largest landslides in history triggered a powerful sideways-directed blast. Ferocious explosions followed and formed an immense mushroom cloud. Late that afternoon, the volcano slowed, but more chaos was about to strike as the eruption had triggered another destructive process. Hot volcanic ash had melted the snowfields on top of Mount St. Helens. Hundreds of tons of meltwater mixed with soil and formed a series of mud flows that cascaded down the slopes.
Most people don't realize that this hazard can affect people living so far downstream, because up to 100 miles from a volcano can still be a hazard zone for these kind of volcanic mud flows.
The biggest of the mud flows came down the Toutle River Valley. On its way there, it reached record speeds of 90 miles per hour and raced over hills as high as 20-story buildings. It destroyed a total of 27 bridges, nearly 200 homes, and more than 185 miles of highway and roads. Today, its remains are still preserved on the banks of the Toutle River.
This deposit is an excellent example of what we scientists call a lahar, but other people refer to as a mud flow. Big, massive flow of material that's much like wet concrete that was coming down the river as a huge wall of material, pushing logs and debris in front of it.
At first, it was a mystery how this mud flow had become so big. But the rocks provided a clue.
What we see are rocks of different type that have come down from Mount St. Helens. Some of these are actually from the original cone of the volcano that collapsed as the debris avalanche.
Geologists could now piece together what caused these destructive mud flows. These rocks, from high up in the volcano, came from the landslide that had been thrown in the valley in the first minutes of the eruption. When meltwater mixed with the landslide debris, it formed a gigantic mud flow. This incredible torrent lasted till late that night and dumped more than 65 cubic miles of mud along the way. Even 30 years later, proof of its destructive power is still in the field.
These lahars came down and totally buried this forest. We see these standing stumps of trees that are the remains of what is often referred to as a ghost forest. This was buried by this lahar. The trees were killed, and we only see them now because of the erosion of the river, which has come back in and eroded into the bank and uncovered them. So this is a fantastic clue of the power and the destruction of this lahar, which completely inundated this lower valley.
But one deposit further upstream was causing confusion in the investigation. It looked like a lahar deposit, but instead of volcanic rock, it was full of rounded river pebbles.
The scientist who first studied this wasn't sure this was a lahar deposit because it contained so much of this rounded river rock, which is characteristic of streambed deposits and not lahars. But then he realized that it had this very, very hard, compact matrix in it, and it was not bedded or layered in any way, and came to the conclusion this had to be a huge lahar that was probably something on the order of the flow of the Amazon River.
Scientists were stumped. Not only did this deposit have rounded river rock, it was also much bigger than the deposit from the mud flow that tore through the valley on May 18th. If it wasn't part of the 1980 lahar, where did it come from? Geologists decided to investigate further and took samples back to the lab. Radiocarbon dating showed that this deposit swept down the valley 3,000 years ago.
If we had been standing on this spot about 3,000 years ago, we would have first heard a very low rumble that would have gotten louder and louder. And if we hadn't heeded that warning, we would have seen a huge wall of broken trees and debris coming around the river bend, probably at 30 or 40 miles an hour, that would have been hundreds of feet high. And that wall of debris and mud and rock would have then just swept through here like a huge freight train, literally wiping the valley clean of anything in its path.
But where did this ancient monster flood come from? The only place that could have stored that amount of water and rounded rock was Spirit Lake, 35 miles upstream. This discovery was crucial because there was an impending danger that nature would repeat itself. Not only did the landslide that initiated the 1980 eruption flow west into the Toutle Valley, it also went east into Spirit Lake and blocked its exit. As rivers and meltwater kept flowing in, water rose to dangerous levels.
It became a very big wake-up call for the hazards community, because if this sort of flood in lahar had happened in the past, it could happen again. And the 1980 deposit dammed Spirit Lake once again with the same type of weak, unstable dam that had existed in the past.
Authorities had to act quickly. Within a couple of years, Spirit Lake would have filled up again. And had it been allowed to overtop, it would have caused a catastrophic flood just like the one 3,000 years ago.
The Corps of Engineers came in. They immediately devised a plan which involved pumping water out of the lake to keep the lake level stable for the short term. Their long-term solution was to drill a boring through a mountain ridge, creating a permanent drain, so that Spirit Lake could never get above that height, and the danger for an overtopping flood was then eliminated.
Scientists now understood what happened on May 18th. Volcanic rock in mud deposits along the banks of the Toutle River Valley is evidence that gigantic mud flows thundered down Mount St. Helens. And rounded river pebbles in a 3,000-year-old mud deposit became a warning sign that Spirit Lake was able to spill over and cause an even bigger lahar. In the summer of 1980, scientists thought the May eruption was their chance of a lifetime, because major volcanic eruptions in the Cascades happen only once or twice every 100 years. But they were soon to be proven wrong. After 2 decades of inactivity, the mountain began to stir again. The explosion of Mount St. Helens in May 1980 scarred the mountain with a massive crater on its north side. But in the summer after the eruption, the volcano began to rebuild itself. Thick magma slowly rose to the surface and formed a dome inside the crater. Had the activities continued at the same rate, it would have taken about 200 years to rebuild the mountain to its pre-1980 size. But in 1986, magma flows ceased and the volcano died down. Life returned to normal and adapted to the new landscape. Plants and trees took hold in the fertile volcanic soil. Elk and other animals migrated back to the mountain. Then, on September 23, 2004, the ominous rumbling began again and put volcanologists on alert.
The entire Cascade Range in the western U.S. produces, on average, about 2 eruptions every century. So you think, well, that's 1 eruption per career. And St. Helens in the 1980s was ours, and we all assumed that that was it. But we got a second chance.
Mount St. Helens was cooking up another mystery. Small earthquakes became stronger and more frequent. GPS measurements detected that the area around the mountain was sinking.
There was one continuously recording GPS instrument around the volcano, and its code name was JR01. JR01 had not moved in any unusual way right up until the day the earthquake started. And then on that very day, it started to move. It moved toward the volcano and downward, as if that entire area of the crust was sagging down toward the volcano.
The only plausible explanation for the sinking land was that the magma reservoir deep underground was shrinking. In earlier surveys, scientists had detected a vast pool of molten rock 8 miles under the volcano. If it was getting smaller, magma had to be on its way up towards the throat of the volcano. The renewed activities caused widespread concern. Scientists feared another eruption was building up, and they were puzzled what kind of eruption it would be. In search of an answer, scientists turned to St. Helens' early days.
Volcanoes are all very individual. They have individual types of eruptions and traits, and what they've done in the past is what they're going to do in the future.
The key to past eruptions is ancient volcanic rock. Mike Klin has specialized in mapping these old deposits. Southwest of St. Helens, he investigates an area covered with large, dark boulders. A close look reveals the type of eruption they formed in.
We know that this rock came from a lava flow because it has big crystals set in a much finer grained ground mass of little crystals. The big crystals grew in the magma chamber while the magma was deep under the volcano, and the fine grained ground mass, which is tiny crystals, grew when the lava erupted at the surface and froze.
Radiocarbon dating established the rock was born 2,500 years ago. The nature of the eruption it formed in was slow and quiet.
This kind of lava flow erupts from the mountain as a liquid, and it flows down the mountainside under gravity. As it flows away from the mountain, it cools until it becomes so viscous that it can't flow anymore. So that's where it stops, and that's what you see here is the end result of emplacement of this kind of lava flow. So they're not dangerous. You can stand and watch it come down at you.
From deposits like these, scientists could tell that Mount St. Helens had produced a number of quiet lava outpourings in the last 300,000 years. They slowly built up the mountain from a small cluster of rock to a conical-shaped volcano. But northeast of the mountain, Klin finds a different deposit, which tells a story of a much more dangerous episode in St. Helens' past.
We look at this deposit, and there's a couple of characteristics that are important. First of all, that it's very loose, and that it's composed of rock fragments that are all about the same size. Another important characteristic is that the rock fragments are touching each other. There's no material in between them. Well, that tells us that these rock fragments came here by falling out of the air. It's a big explosive eruption that sends the material very high into the sky, and when the wind dies down, they start to fall and they pile up here.
The rock fragments are very light pumice that formed during a violent eruption similar to the one that produced the huge mushroom cloud in May 1980. But age dating revealed that this deposit was much older. This event happened 3,500 years ago, and compared to the 1980 eruption, scientists found evidence that it was much more dangerous and spewed out 4 times more rock and ash.
This is the biggest eruption in Mount St. Helens history, and it was about a cubic mile of material that was erupted at this time. And we know that because we trace out the deposit, measure its thickness and its distance, and you add that all up together and you get the volume of the eruption. This deposit can be traced all the way to central Canada.
Studying Mount St. Helens' past has revealed that she has an unpredictable eruptive nature.
Mount St. Helens had everything from relatively benign lava flows to quite violent eruptions in the past. So it's very hard when a volcano starts acting up to know which of these possibilities is going to happen. And of course, the various scientists, we discuss and argue and all that kind of stuff, what we think is going on. And nobody truly knows what's going on.
Scientists investigating Mount St. Helens have found clues that show different eruptive behaviors in her past. Large, dark boulders are evidence that she is able to produce slow and quiet eruptions. A thick deposit of white pumice is evidence for an ancient, dangerous eruption 4 times larger than the one in 1980. Fortunately, the events that began in 2004 took a lucky turn. The magma did reach the surface, but it had lost its explosive power. It flowed out like toothpaste in a dome-building style of eruption. As geologists carried on studying Mount St. Helens, a volcano 4,000 miles away began to stir. Because of their experience in 1980, scientists were convinced a major catastrophe was about to unfold. And this time, 12,000 lives were at risk. The eruption of Mount St. Helens in May 1980 took scientists by surprise. It was the first time they witnessed the failure of a massive bulge, a huge landslide, and a powerful lateral blast.
Prior to 1980, we just didn't have the knowledge to make those kinds of specific predictions. We started learning in the 1980s at St. Helens. We've continued to learn at volcanoes around the world, and we've had some successes.
Forecasting volcanic eruptions is difficult because there is no strict pattern to the buildup. But as scientists are getting more experienced in observing volcanic behavior, they are getting better at their predictions. In 1995, Soufriere Hills volcano on the Caribbean island of Montserrat became restless. It had been quiet for 350 years until earthquakes rumbled it to life again. Residents were used to a gently steaming mountain and simply hoped it would die down. But when the earthquakes got stronger, officials called for help. A team of U.S. volcanologists flew to the Caribbean to monitor the reawakening.
There developed a situation there whereby there was a region of high seismicity occurred just as St. Helens. If you went up on the mountain, as we did, and just about knocked you to your knees, there were very strong events.
Strong earthquakes weren't the only warning signs. On the south side of the mountain, they observed how a monstrous bulge began to form.
There were cracks that were occurring. You could see the cracks were moving every day. It looked like the whole side could fall apart. So we could get a slope collapse there, a major slope collapse.
By October 1997, the bulge was growing at a staggering rate of 280 cubic feet per second. Scientists were alarmed. Because of their experience on Mount St. Helens, they knew that a collapse of the bulge was imminent. People living in the proximities of the volcano were in danger. So they advised the authorities to evacuate immediately. 8,000 people had to leave the island. Over 4,000 were forced to move to a safer location to the north. On the 26th of December, 1997, the volcano struck. After an intense swarm of earthquakes, a huge part of the bulge broke loose and roared down the valley. Like at Mount St. Helens, the sudden removal of rock released the pressure on the magma below. A lateral blast surged south and spawned a vertical ash column 36,000 feet high. Within 15 minutes, the eruption destroyed 4 square miles of the island and completely buried the island's capital, Plymouth, under 39 feet of mud. Montserrat is a prime example where lessons learned from a big catastrophe have prevented another one.
Almost everything that occurred at St. Helens did occur at Montserrat. It replicated St. Helens not only in the lateral blasts and so forth, but it did everything that St. Helens did on a smaller scale.
Scientists studying the eruption of Mount St. Helens on May 18, 1980, have uncovered a sequence of events they had never seen before. A growing bulge on the north flank of the mountain was an alarming sign that a pool of magma was building up within the volcano. Gray volcanic rock from the bulge 5 miles away was evidence for a powerful sideways eruption. A 3,000-year-old mud deposit became a warning sign that the valleys around the mountain have been repeatedly swamped by huge mud flows. A deposit of white pumice rock found all the way up to Canada showed that Mount St. Helens is able to produce eruptions 4 times larger than the one in 1980. As the investigation has shown, Mount St. Helens is full of surprises.
St. Helens, I think of it as a teenager among the Cascade volcanoes. It's young, it's vigorously active, it's explosive, it's very energetic. Even though to our eye, as we look at it, it appears to be sleeping, it's active, it's doing what it's been doing for tens of thousands of years.
Mount St. Helens looks set to continue her erratic and at times violent outbursts. Her deadly potential is a stark reminder the Earth is never at rest.